The Sun, our life-giving star, is far more than a glowing ball of gas in the sky. It is a massive fusion reactor, an enormous sphere of hydrogen and helium where nuclear reactions forge energy at unimaginable scales. This energy radiates outward, providing the light and warmth essential for life on Earth, shaping climates, oceans, and ecosystems. Like all stars, the Sun is not eternal. It has a life cycle, born from a dense cloud of gas and dust, maturing into a stable fusion-powered star, and eventually evolving into the final stages of its existence. Over billions of years, it undergoes profound transformations, affecting every planet and object within its gravitational embrace. Studying the Sun's life and eventual death allows us to glimpse the fate of the solar system itself, offering insight into cosmic cycles of creation and destruction that have repeated throughout the universe for eons. The Sun's current stage, known as the main sequence, represents the longest and most stable period in its life cycle. During this phase, the Sun is essentially a colossal nuclear furnace, fusing hydrogen nuclei into helium deep within its core. This process, known as nuclear fusion, occurs under extreme pressures and temperatures, reaching approximately 15 million degrees Celsius at the core. Hydrogen atoms collide with such force that they overcome their natural electrostatic repulsion, combining to form helium. Each fusion reaction releases an enormous amount of energy in the form of gamma rays, which gradually make their way to the Sun's surface over thousands of years, before escaping as the sunlight we see and feel on Earth. This fusion not only powers the Sun, but also sustains the balance between the inward pull of gravity and the outward pressure from nuclear reactions, maintaining the Sun's stability and size during this stage. This main sequence phase is a remarkably prolonged period in the Sun's life, expected to last roughly 10 billion years in total. Having formed around 4.6 billion years ago, the Sun is currently about halfway through this stable stage. During this time, it maintains a nearly constant luminosity and size, creating a predictable environment for the planets orbiting it. The main sequence is often described as the prime of life for a star, where it shines consistently and provides the energy necessary to support planetary systems. The predictability of this phase has allowed life to thrive on Earth, as temperatures, climate cycles, and solar radiation levels remain relatively steady over geological timescales. Stars much more massive than the Sun burn their fuel faster, living shorter but brighter lives, while smaller stars like red dwarfs burn slowly, existing for tens to hundreds of billions of years. Our Sun's mass and composition have positioned it perfectly to sustain a long period of stability, which is vital for understanding the eventual impacts of its aging process on the solar system. The fusion of hydrogen into helium is not uniform throughout the Sun. In the core, where temperatures and pressures are highest, fusion occurs most efficiently. As helium accumulates in the core, hydrogen in the surrounding shell continues to burn, contributing to the energy output of the Sun. This gradual buildup of helium, however, is a subtle harbinger of the Sun's eventual aging. Over billions of years, the accumulation of helium in the core causes changes in the Sun's structure. The core slowly contracts under gravity as the hydrogen supply diminishes, leading to a slight increase in temperature and pressure. This, in turn, accelerates the fusion rate in the surrounding hydrogen shell, making the Sun gradually brighter and hotter, a change so slow that it is imperceptible on human timescales, yet significant when considered over millions or billions of years. The energy produced in the main sequence phase is not only what sustains life on Earth, but it also drives the solar phenomena we observe today. Sunspots, solar flares, and the solar wind are all manifestations of the complex magnetic interactions and energy flows originating from the fusion processes within the Sun. Sunspots are cooler, darker regions on the Sun's surface caused by concentrated magnetic activity, while solar flares release bursts of energy and particles into space. The solar wind, a continuous stream of charged particles, flows outward through the solar system, affecting planetary magnetospheres and shaping the space environment around Earth. Without the main sequence fusion process, these dynamic phenomena would not exist, and the solar system would be drastically different. As the Sun continues to fuse hydrogen into helium, small yet detectable changes are slowly occurring. The Sun's luminosity has increased by nearly 30% since its formation, a trend that will continue as it ages. This gradual brightening will have profound implications for the inner planets over the next billion years, eventually causing surface temperatures on Earth to rise, oceans to evaporate, and the climate to become inhospitable to life as we know it. While these changes are imperceptible now, they are inevitable markers of the Sun's aging process, signaling the approach of more dramatic transformations that will culminate in the next stages of its life cycle. Understanding the main sequence phase is crucial because it sets the stage for the red giant phase, during which the Sun's structure, luminosity, and size will change drastically, reshaping the solar system and threatening the very existence of Earth as we know it. The Sun's main sequence is more than a period of stability. It is a delicate balancing act maintained over billions of years. This stage exemplifies the intricate relationship between gravity and nuclear fusion, between pressure and energy output, and between a star and the planets that depend on it. The hydrogen to helium fusion process is not only the engine that powers the Sun today, but also the fundamental process that dictates its future evolution. As the core gradually accumulates helium and the hydrogen fuel diminishes, the Sun will reach a tipping point where the stable equilibrium of the main sequence can no longer be maintained. At this juncture, the subtle changes now occurring will intensify, leading to the dramatic expansion and transformation into a red giant, a phase in which the Sun's influence will grow far beyond its current radius, fundamentally altering the inner solar system and setting the stage for the eventual fate of Earth and its neighboring planets. It is in this context that astronomers and astrophysicists study stars of various ages and masses to predict the Sun's future. Observing older stars, similar in mass and composition to the Sun, allows scientists to model the processes that will take place in our solar system in the distant future. These models show that as the Sun exhausts its hydrogen fuel, the balance between the gravitational pull of its mass and the outward pressure from fusion will be disrupted. This will initiate a cascade of changes, leading to swelling, increased luminosity, and ultimately a transformation that will engulf the inner planets. Understanding the Sun's main sequence provides the foundation for these predictions and frames our comprehension of the delicate interplay between stellar evolution, planetary survival, and the conditions required for life. Every photon emitted from the Sun today carries with it the story of nuclear fusion, the energy sustaining life, and the subtle march of time that will ultimately lead to the Sun's dramatic demise. Even while the Sun remains in its main sequence phase, subtle yet inexorable signs of aging are already underway, marking the early steps of its long journey toward transformation. Though it continues to shine steadily, providing life-sustaining energy to Earth, the Sun is not entirely static. Over billions of years, as hydrogen in the core is converted into helium, the internal composition and structure of the Sun gradually shift. This slow but relentless change has measurable consequences. The core, now richer in helium and depleted of hydrogen, contracts slightly under gravity, which in turn raises the temperature and pressure within. As the core heats up, the fusion rate in the surrounding hydrogen shell increases, producing more energy. This results in a gradual increase in the Sun's overall luminosity and temperature, a phenomenon astronomers have been able to quantify and project with remarkable precision. Currently, the Sun is approximately 30% brighter than it was at its birth 4.6 billion years ago, and this brightening trend will continue throughout the remainder of its main sequence. While this might seem insignificant on human timescales, even minor increases in solar energy have profound implications for Earth. Over the next billion years, models predict that the Sun's increasing luminosity will raise surface temperatures on our planet, gradually causing the oceans to evaporate, altering weather patterns and placing stress on the biosphere. These changes, imperceptible day to day, are cumulative and unavoidable. They serve as early indicators of the Sun's inevitable progression toward its red giant phase, providing a preview of the more extreme transformations yet to come. Alongside increasing brightness, the Sun's surface temperature is also subtly climbing. Currently averaging around 5,500 degrees Celsius, the Sun's photosphere, the visible surface layer, has warmed slightly over its lifetime and will continue to do so as core fusion accelerates. This rise in surface temperature is accompanied by small shifts in solar activity, including fluctuations in sunspot cycles, magnetic field intensity, and solar flare frequency. These phenomena, while mostly cyclic and seemingly regular, are influenced by the underlying changes in the Sun's internal structure, acting as a window into the subtle dynamism of an aging star. Increased solar activity can affect not only the Earth's upper atmosphere, but also the behavior of planetary magnetospheres and the heliosphere, the protective bubble of solar wind that extends through the solar system. Another subtle sign of the Sun's aging is the gradual expansion of its outer layers. While still relatively stable in size compared to the dramatic swelling that will occur in the red giant phase, the Sun is slowly increasing in radius over geological timescales. This is a direct consequence of the rising temperature in the core, which increases the outward radiation pressure, causing the outer envelope to expand incrementally. As the Sun expands and brightens, it gradually alters the gravitational balance within the solar system, affecting the orbits of the inner planets ever so slightly. Mercury, Venus, and Earth experience tiny changes in their orbital dynamics, and while these shifts are negligible today, they hint at the larger, more chaotic interactions that will unfold as the Sun enters its next evolutionary stage. Helioseismology, the study of solar vibrations, has provided scientists with an extraordinary tool to observe these subtle aging processes. By analyzing waves traveling through the Sun's interior, astronomers can infer changes in density, temperature, and composition over time. These measurements reveal that the Sun's core is slowly becoming more compressed and helium-rich, a process that subtly alters the way energy is transported to the surface. Even the pattern of convective cells in the Sun's outer layers, responsible for transporting heat and generating magnetic fields, is slowly evolving, reflecting the deep internal changes occurring as the star ages. Every measurement, every observation of sunspots, solar flares, or luminosity shifts is a testament to the Sun's dynamic evolution, even in this stable main sequence phase. The aging of the Sun is not merely a scientific curiosity, it is intimately tied to the long-term fate of the solar system. The gradual brightening and warming influence planetary climates and atmospheric compositions, setting the stage for the eventual loss of habitability on Earth. These subtle changes, accumulated over hundreds of millions to billions of years, foreshadow the radical upheavals that will occur when the Sun leaves the main sequence. They serve as a reminder that stars are not immutable beacons, but dynamic engines of change, whose life cycles are written into the orbits, climates, and very existence of their surrounding worlds. The incremental shifts in luminosity, temperature, magnetic activity, and size may seem modest today, but in cosmic terms, they are the quiet prelude to a cataclysmic transformation. Eventually, these signs of aging will intensify as the Sun approaches the threshold where hydrogen in the core becomes insufficient to sustain equilibrium. The outer layers will respond by expanding further, while the core contracts and heats up more rapidly. This process marks the transition from the relatively calm main sequence phase to the dramatic red giant phase, where the Sun's energy output will surge and its radius will grow to encompass planets that currently orbit safely at a distance. The early signs of aging we observe now, gradual increases in luminosity and temperature, subtle expansion, and evolving solar activity, are the faint echoes of the colossal changes to come. They provide a critical window into the processes that govern stellar evolution, offering both a scientific roadmap for predicting the Sun's future and a sobering reflection on the impermanence of the solar system as we know it. In the context of planetary impact, even these incremental changes are far from trivial. Increased solar radiation will gradually strip atmospheres from closer planets, exacerbate climate extremes, and alter orbital resonances over long timescales. Comets and asteroids in the inner solar system may experience modified trajectories due to shifts in solar mass distribution and radiative forces, subtly reshaping the architecture of the solar system long before the Sun's final acts. Understanding these signs of aging provides crucial insights not only into stellar physics, but also into planetary dynamics, the long-term viability of life, and the interconnected fate of all bodies within the Sun's gravitational domain. As the Sun's core continues to accumulate helium and hydrogen in the surrounding shell becomes increasingly exhausted, the delicate equilibrium that has maintained its size and brightness during the main sequence will begin to falter. This marks the onset of one of the most dramatic transformations in the life of a star, the red giant phase. At this stage, the core, now primarily composed of helium, contracts under gravity and heats up, while the outer layers respond by expanding enormously. The Sun's radius will increase hundreds of times its current size, swelling far beyond its present orbit, and dramatically altering the architecture of the solar system. Planets that currently orbit at relatively safe distances will find themselves perilously close to the expanding stellar envelope, and some may even be engulfed entirely. The red giant phase represents not only a colossal increase in size, but also a fundamental shift in the Sun's energy output. As the star expands, its surface temperature will actually decrease compared to the main sequence, giving it a characteristic reddish hue. Yet the total luminosity, the energy radiated into space, will increase significantly. This duality, a cooler surface with dramatically higher output, arises because the enormous increase in surface area compensates for the slightly lower surface temperature. The result is a Sun that dominates the inner solar system in both size and intensity, radiating enough energy to destabilize planetary atmospheres, boil oceans, and render previously habitable zones unlivable. Mercury, being the closest planet, will almost certainly be consumed entirely, while Venus is expected to follow. Earth's fate is more uncertain, hinging on complex interactions between the Sun's mass loss, tidal forces, and orbital dynamics. But even if it avoids being engulfed, it will be scorched beyond recognition. As the Sun transitions into a red giant, the inner planets will not only face potential engulfment, but will also experience significant orbital perturbations. As the Sun loses mass through powerful stellar winds, streams of particles flowing outward at incredible speeds, the gravitational pull it exerts on the planets will weaken. This reduction in gravitational force will cause the orbits of the remaining planets to expand. While this may offer a narrow window of salvation for Earth, increasing its distance from the swelling solar envelope, it will not protect the planet from the searing heat and radiation. The expansion of the Sun's outer layers, combined with its intensifying luminosity, ensures that the inner solar system becomes a region of extreme thermal stress, where rocky planets and moons are either consumed, scorched, or stripped of their atmospheres. The process of expansion is gradual on human timescales, but incredibly fast in astronomical terms, occurring over tens to hundreds of millions of years. During this period, the Sun's radius will grow to a size large enough that if placed at the center of our current solar system, it would extend past the orbit of Mercury and Venus, possibly reaching Earth. The outer layers of the Sun will become tenuous and convective, with immense surface activity, including giant solar prominences and powerful flares. This convective behavior, combined with the extreme expansion, drives strong stellar winds that blow material away into space, contributing to the Sun's mass loss and altering the dynamics of the solar system. The red giant Sun, swollen and luminous, will dominate the sky, a burning sphere hundreds of times larger than the Sun we see today. One of the most dramatic consequences of the red giant expansion is the effect on planetary surfaces. Even planets that are not engulfed will experience extreme heating. Oceans will evaporate, atmospheres will be stripped, and surface rocks may melt under intense solar radiation. The inner solar system will be transformed into an inferno, a place where previously familiar landscapes and environments are obliterated. The expansion phase also triggers tidal interactions with surviving planets, causing orbital instability and potential collisions among smaller bodies, like asteroids and dwarf planets. The combined effects of expansion, heat, radiation, and gravitational reshuffling ensure that this phase represents a radical restructuring of the solar system, the first visible step in the Sun's journey from life-giving star to dying ember. This red giant stage is a universal process among stars of the Sun's mass. While the Sun will not explode as a supernova, its expansion is no less dramatic in its immediate vicinity. Observations of aging stars in our galaxy provide vivid examples of what lies ahead. Stars bloated to enormous sizes, their surfaces cool yet radiating extraordinary luminosity, shedding their outer layers in streams of gas and dust. These observations allow astrophysicists to predict not only the scale of expansion, but also the environmental conditions for the inner planets. In the case of Earth, this phase will mark the end of its long-standing stability, transforming the planet from a habitable world into a scorched, barren orb, or erasing it entirely from existence. The red giant phase will also initiate the next stages of solar evolution, as helium fusion ignites in the core, setting the Sun on the path toward shedding its outer layers and creating a planetary nebula. But long before this final act, the expansion itself will reshape the inner solar system irrevocably. It is during this swelling, glowing, and violently active phase that the Sun will announce, in the most tangible way possible, that even seemingly eternal stars are transient, their fates written in the processes of physics and time. The engulfment of planets, the immense heating, and the transformation of familiar worlds into hostile wastelands are all part of the natural progression from stable star to dying giant, a monumental spectacle that dwarfs the scale of human history. As the Sun fully enters its red giant phase, one of the most dramatic and devastating changes will be the surge in both temperature and luminosity, transforming the inner solar system into an environment of extreme heat and radiation. While the surface temperature of the Sun will actually drop slightly compared to its main sequence average, giving it the reddish hue that defines red giants, the total energy output will increase exponentially. This happens because the star's radius expands hundreds of times its current size, vastly increasing its surface area. Even with a cooler surface, the immense increase in area means the Sun will radiate far more energy than it does today, inundating the inner planets with heat and light at levels unimaginable to modern life. For Earth, Venus and Mercury, this surge represents a catastrophic shift. Planetary surfaces that once supported oceans and atmospheres will now face relentless thermal bombardment. For Earth, the consequences are particularly severe. The oceans, which regulate climate and support life, will begin to evaporate as the planet receives a significantly greater influx of solar energy. Rising temperatures will trigger a runaway greenhouse effect, accelerating the loss of water vapor into space and stripping the atmosphere of lighter molecules. Surface temperatures could soar to hundreds or even thousands of degrees Celsius, boiling away any remaining liquid water and rendering the planet incapable of sustaining any known forms of life. Venus may already be consumed or in the final stages of atmospheric loss, while Mercury will have long been engulfed by the expanding Sun. Even if Earth narrowly avoids direct engulfment, the surge in luminosity ensures it will be reduced to a barren, molten landscape, its once familiar climate obliterated by the intensified heat. The surge in luminosity also has profound implications for nearby moons and smaller bodies within the inner solar system. Satellites orbiting planets or traveling through space may experience surface heating sufficient to melt ices and volatiles, fundamentally altering their composition. Comets and asteroids, especially those rich in volatile ices, will sublimate rapidly, contributing gas and dust to the increasingly turbulent environment around the Sun. This material, carried by the intensifying solar wind, adds to the mass loss from the Sun and begins the early stages of what will become the formation of a planetary nebula. The red giant phase is not just a local catastrophe for the inner planets. It initiates a chain reaction of heating, mass ejection, and orbital perturbations throughout the solar system. The increase in solar energy output will be staggering. Estimates suggest that the Sun could become thousands of times more luminous than it is today, a transformation that changes the very physics of the solar neighborhood. The habitable zone, the region where liquid water can exist, will shift far outward, potentially reaching the current orbits of Mars or even Jupiter. Regions that were once frozen and inhospitable may experience temporary warming, but these effects are short-lived on the cosmic scale as the Sun's expansion continues and inner planets are either consumed or rendered uninhabitable. For Earth, this means that any chance of maintaining conditions suitable for life disappears long before the Sun fully engulfs the planet, emphasizing the scale of destruction inherent in this phase. The thermal effects of the red giant Sun are not limited to surface heating. Intense radiation, including ultraviolet and X-rays, will bombard planetary atmospheres, accelerating chemical reactions that break down molecular bonds and strip away protective layers. The upper atmosphere of Earth will be eroded, losing lighter elements into space, while heavier elements may remain briefly before being consumed or scattered. This process of atmospheric stripping is amplified by the extreme solar wind emanating from the swollen Sun, which will blow at velocities much higher than those experienced during the main sequence. The combination of thermal radiation and particle bombardment ensures that no inner planet retains the conditions that once made it habitable. Oceans boil away, atmospheres are torn apart, and the familiar surface features of rocky planets are fundamentally altered or erased. From an observational standpoint, the surge in luminosity of the red giant Sun is not merely destructive. It is also a magnificent cosmic spectacle. The Sun will dominate the sky in brightness, far outshining all other celestial bodies visible from any surviving planet. If one were able to safely observe from a distant orbit or from an interstellar vantage point, the Sun would appear as a vast glowing orb, its immense surface radiating energy across a broad spectrum. The colors and intensity of this radiation will be unlike anything experienced during the main sequence, bathing the solar system in an extraordinary, almost theatrical light display. This stage underscores the paradoxical nature of stellar death. Even as the Sun brings destruction to its planetary companions, it simultaneously creates one of the universe's most brilliant displays of energy. The surge in temperature and luminosity also accelerates chemical and geological processes on planetary surfaces. Rocks may melt and form molten seas. Previously frozen compounds become reactive gases, and minerals are vaporized and redistributed into space. For any remaining planetary crusts, this period may be their final formative stage, reshaping surfaces in ways that will leave lasting traces long after the Sun has shed its outer layers. While the red giant phase will last only a fraction of the Sun's total lifespan, on the order of a few 100 million years, it is a period of intense and irreversible transformation for the inner solar system, where the familiar order of planets and surfaces is fundamentally disrupted by the surge in stellar energy. The red giant's heating and brightening also signal the approaching climax of the Sun's life cycle. Following this stage, helium fusion will ignite in the core, releasing yet more energy and further altering the Sun's structure. The interplay of rising luminosity, extreme heat, and the star's evolving core composition sets the stage for the subsequent shedding of outer layers and the eventual formation of a planetary nebula. The inner planet's fate, largely sealed by the combination of engulfment, surface heating, and atmospheric stripping, illustrates the unstoppable power of stellar evolution. This phase represents a vivid demonstration of the cosmic forces that govern star and planet interactions, revealing the intimate connection between a star's life cycle and the environment of its orbiting worlds. As the Sun swells into a red giant and its luminosity and heat surge, the inner solar system will descend into a period of profound chaos. The combination of the Sun's expanding outer layers, intense radiation, and strong stellar winds will destabilize planetary orbits and trigger collisions among smaller bodies. Mercury, already on the brink of being engulfed, will almost certainly be consumed entirely, its material stripped into space and contributing to the Sun's expanding envelope. Venus, only slightly farther from the Sun, faces a similar fate. Intense heat and tidal forces may strip it of its atmosphere, melt its surface, and ultimately drag it into the Sun's convective outer layers. Earth's survival is more precarious. While its orbit may expand due to the Sun's mass loss, the gravitational interplay with neighboring planets and the tidal forces from the swelling star could destabilize its trajectory, potentially sending it into a fatal collision course with Venus, or even with fragments of the inner planets disintegrating under solar stress. The red giant Sun will exert enormous tidal forces on all inner planets, stretching and compressing them in ways unimaginable under the current main sequence conditions. These tidal interactions will alter orbital dynamics, potentially causing resonances and shifts that make planetary paths increasingly erratic. Orbits that were once stable over billions of years will become more eccentric, bringing planets closer to or farther from the star in unpredictable ways. This orbital chaos is amplified by the Sun's mass loss. As it sheds material through intense solar winds, the gravitational grip on the planets weakens, allowing their orbits to drift outward. For some planets, this outward migration may offer a temporary reprieve from engulfment, but for others, it may induce collisions with neighboring planets or moons as their paths cross or intersect due to shifting gravitational influences. Asteroids and smaller celestial bodies in the inner solar system will also be profoundly affected. The asteroid belt, located between Mars and Jupiter, may experience heightened instability due to gravitational perturbations from the expanding Sun and shifting orbits of planets. Collisions among asteroids could become more frequent, generating vast amounts of debris that may either fall into the Sun, impact surviving planets, or be expelled into interstellar space. Comets traveling from the outer solar system into the inner regions will face intensified solar radiation, causing them to sublimate rapidly and disperse clouds of gas and dust, adding to the chaos of the inner solar environment. The inner solar system will essentially become a dynamic and violent zone, where planetary surfaces, atmospheres, and orbits are continuously reshaped by both gravitational forces and stellar influence. The gravitational consequences extend beyond the inner planets. As the Sun loses a substantial portion of its mass through strong stellar winds, the balance of gravitational forces across the solar system will shift. Outer planets like Mars, Jupiter, and Saturn will gradually drift into slightly larger orbits. While this outward movement reduces the likelihood of these planets being engulfed, it also introduces a ripple effect on orbital resonances, potentially destabilizing moons, rings, and minor bodies in their vicinity. Some moons may escape entirely, becoming rogue objects traveling independently through the solar system, while others could collide with each other or be ejected into highly elliptical orbits. The red giant Sun, by altering its mass distribution and radiative pressure, transforms the entire solar system into a more dynamic and less predictable environment. Planetary collisions are a particularly dramatic aspect of this chaos. As smaller planets and moons experience increased eccentricity in their orbits, intersections and near misses become more likely. Rocky planets that survive the initial engulfment phase may encounter debris or even collide with neighboring planets, creating catastrophic impacts that can reshape planetary surfaces or break them apart entirely. These collisions release vast amounts of energy, vaporizing rock and sending shockwaves through remaining atmospheres, further compounding the destruction wrought by the Sun's expanding envelope. The inner solar system, once relatively stable and predictable, becomes a realm dominated by high-energy interactions, violent reshaping, and a relentless march toward cosmic reconfiguration. The red giant's influence on planetary rotation and axial tilt should not be underestimated either. Tidal forces and differential heating will induce strong torques on surviving planets, potentially altering their spin rates and axis orientation. This could result in extreme day-night cycles, severe seasonal variations, and enhanced tectonic activity if molten cores remain active under such stress. Surface conditions, already made hostile by extreme temperatures, will be further destabilized by these mechanical effects, creating a chaotic planetary environment where survival of any existing structures or remnants of life is highly unlikely. Even geological and atmospheric processes, such as volcanic outgassing or crustal deformation, will be driven into extremes, leaving behind worlds that are unrecognizable compared to their pre-red giant state. The inner solar system's chaos is not only a story of destruction, but also a prelude to the Sun's later life stages. Material stripped from planets and moons will form diffuse clouds of gas and dust around the dying star, contributing to the eventual formation of a planetary nebula. Collisions between debris fragments, planetary cores, and molten layers enrich the surrounding space with heavy elements, laying the groundwork for future stellar generations. In this way, the destruction wrought by the red giant phase is intimately tied to cosmic recycling. The violence and chaos serve as both an end and a beginning, seeding the environment with the raw materials for new celestial bodies long after the Sun itself has ceased to shine brightly. By the time the Sun completes its red giant expansion, the inner solar system will be almost unrecognizable. Mercury and Venus will likely have been engulfed. Earth may be scorched or destroyed, and the asteroid belt and smaller bodies will be scattered or transformed. Orbital shifts, collisions, and debris will leave the region in a state of tumult, highlighting the immense power a dying star can exert over its planetary domain. The Sun's transformation into a red giant exemplifies how the life cycle of a star directly shapes the fate of its planets, illustrating the interplay between stellar evolution, gravitational dynamics, and the inevitable chaos that accompanies the death of a star. As the Sun swells into its red giant phase, one of the most dramatic and far-reaching forces it exerts is the intensification of its stellar winds. These winds are streams of charged particles, primarily protons and electrons, that are expelled at immense velocities from the Sun's outer layers. While the solar wind exists today, gently streaming through the solar system at speeds of roughly 400 to 800 kilometers per second, the red giant phase magnifies this phenomenon to extraordinary levels. The expansion of the Sun's outer layers, combined with the increased luminosity and surface activity, drives a torrent of particles outward, stripping mass from the Sun itself, while simultaneously exerting tremendous pressure on the surrounding planets and debris. These powerful stellar winds are more than mere gusts of particles. They are agents of transformation, capable of reshaping the solar system and carrying material across vast distances in space. The effects of these intensified solar winds on the inner planets are catastrophic. Mercury and Venus, likely already engulfed or destabilized, are further stripped of any remaining atmospheric or superficial material. Even for planets that avoid being swallowed directly by the expanding Sun, such as a potentially surviving Earth, the effects are extreme. The high-energy particles collide with planetary atmospheres, gradually eroding them and carrying lighter gases away into space. This process, known as atmospheric stripping, accelerates the loss of water vapor, carbon dioxide, nitrogen, and other essential components of an atmosphere, leaving behind barren rock. For moons and smaller bodies, which lack substantial gravitational fields to retain their gases, the stellar winds are even more effectively peeling away outer layers, vaporizing ices, and contributing to a cloud of material surrounding the star. The stellar winds also play a crucial role in distributing planetary material across the solar system. As outer layers of planets, moons, and asteroids are eroded, gas and dust are carried outward, forming expanding shells of matter around the Sun. This ejected material, consisting of hydrogen, helium, heavier elements, and even partially vaporized rock, contributes to the formation of the future planetary nebula. The process of mass loss through stellar winds transforms the environment of the solar system, enriching the surrounding space with raw elements that will later participate in cosmic recycling. Essentially, the Sun's winds act as both a destructive and creative force. They disassemble planetary surfaces while simultaneously providing the seeds for future stars and planetary systems. The intensity of these winds is staggering in the red giant phase. Models suggest that the Sun could lose up to 30 to 40% of its total mass through stellar winds during this stage. This loss of mass not only fuels the redistribution of matter, but also directly affects the orbits of surviving planets. As the Sun's gravitational pull weakens due to mass loss, planetary orbits expand, sometimes dramatically. This outward migration may prevent complete engulfment for certain planets, but it also destabilizes their trajectories, increasing the risk of collisions among debris or interactions with other planetary bodies. The solar winds, therefore, act as both sculptor and disruptor, reshaping the solar system in real time. These winds are further amplified by the Sun's convective outer layers. In the red giant phase, the Sun's envelope becomes highly turbulent, with massive convective cells transporting energy from the interior to the surface. These convective motions, combined with magnetic activity, drive violent ejections of matter, known as coronal mass ejections, CMES, on a scale far larger than anything currently observed in the Sun. CMEs in this phase can carry billions of tons of plasma outward, interacting with planetary magnetic fields, stripping atmospheres, and redistributing material over millions of kilometers. The interplay of radiation pressure, gravitational forces, and high-energy particle streams ensures that no inner planet remains unaffected, and even distant asteroids and comets are nudged or dispersed from their previous orbits. Stellar winds also dramatically impact icy bodies in the outer solar system. Comets, Kuiper belt objects, and distant dwarf planets experience increased sublimation as the Sun radiates more energy and particles. The solar wind strips volatile ices, forming extensive tails and clouds of dust that stream across the solar system. These particles, mixed with material from inner planets, contribute to a complex and evolving environment that will ultimately coalesce into the planetary nebula, following the Sun's helium burning and mass loss phases. In essence, the solar winds are a conveyor belt of matter, redistributing elements from the heart of the solar system to its outer reaches, sowing the seeds for the next generation of celestial bodies. The effects on smaller bodies, such as moons and asteroids, illustrate the pervasive reach of these winds. Tidal interactions combined with bombardment by charged particles weaken structural integrity, causing fragmentation and vaporization. Dust and gas from these events are swept into expanding shells around the Sun, which will later glow as part of the planetary nebula. Even the surviving cores of inner planets are bombarded by energetic particles, stripping surface layers and contributing further to the cosmic cycle of destruction and creation. The Sun's stellar winds, in essence, act as a universal eraser, removing layers, destabilizing orbits, and redistributing material in preparation for its final evolutionary stages. The fate of Earth as the Sun enters its red giant phase remains one of the most compelling and uncertain questions in astronomy, blending physics, celestial mechanics, and sheer cosmic scale into a scenario that challenges human imagination. While Mercury and Venus face near certain destruction through engulfment or vaporization, Earth occupies a precarious middle ground. Its ultimate end depends on the delicate interplay between the Sun's expansion, mass loss, tidal forces, and the intricate dynamics of orbital mechanics. Though precise predictions are difficult, current models offer a range of possible outcomes, each of which paints a stark portrait of a planet that will no longer resemble the world we know today. One possibility is that Earth will be engulfed by the expanding Sun. As the red giant's radius swells, estimates suggest it could extend out to or slightly beyond Earth's current orbit. If the outward migration of the orbit caused by the Sun's mass loss is insufficient to compensate for the expansion, Earth could be pulled into the Sun's outer layers. In this scenario, the planet would not merely be scorched. It would undergo a slow, excruciating disintegration. Its crust and mantle would vaporize under intense heat. Oceans would boil away almost instantly, and the remaining material would mix into the Sun's convective envelope. Any remnants of Earth's solid core would eventually be absorbed or ejected into space by turbulent solar processes, leaving no trace of the planet as a coherent body. This outcome, though extreme, is considered a real possibility and represents the ultimate illustration of the Sun's destructive potential during its red giant phase. Another scenario suggests that Earth may narrowly avoid direct engulfment, but still be devastated by extreme heat and tidal forces. In this case, the planet's orbit could expand outward as the Sun loses mass through stellar winds, potentially sparing it from being physically consumed. However, this is far from a salvation. Even at a slightly greater distance, Earth would be subjected to extreme luminosity and temperatures, boiling away oceans, stripping the atmosphere, and triggering catastrophic climate instability. Surface rocks might partially melt, tectonic activity could accelerate, and the biosphere would be eradicated long before any final encounter with the Sun's outer layers. In essence, even if Earth survives the red giant physically, it will have become a barren, lifeless, molten landscape, stripped of all the conditions that once supported life. The planet would exist in name only, a shell of its former self orbiting a dying star. A more nuanced possibility involves the complex interplay of tidal forces and angular momentum transfer. As the Sun's envelope expands, gravitational interactions may alter Earth's orbit in ways that either push it outward or, counterintuitively, draw it inward, depending on the timing and intensity of tidal interactions. Some simulations suggest that tidal drag from the Sun's convective envelope could gradually decelerate Earth's orbital motion, spiraling it closer to the engulfing layers, while other models indicate that mass loss from the Sun could push the planet outward just enough to survive. The uncertainty of these outcomes underscores the chaotic and delicate nature of stellar planetary interactions at this stage. Even minor variations in timing, mass loss rate, or initial orbital parameters could tip the balance between total destruction and a marginal survival scenario. The atmospheric and surface consequences for Earth in either scenario are catastrophic. Before any potential engulfment, rising solar radiation will trigger a runaway greenhouse effect, driving water vapor into the upper atmosphere, where it is stripped away by the intensified solar wind. Oceans will evaporate entirely, leaving the surface arid and molten. Any remaining atmosphere will be progressively lost to space as lighter molecules are blown away, leaving behind a tenuous, unbreathable layer of heavier gases for a brief period before total dispersal. Volcanism may continue temporarily, fueled by internal heat, but this will do little to offset the overwhelming energy influx from the Sun. In short, whether or not Earth is physically engulfed, it will be unrecognizable, a scorched relic orbiting a dying star. Even the planet's core is not entirely safe. If Earth survives the initial expansion phase without being swallowed, it may still undergo severe geological and chemical alterations. Surface and crustal material may melt and vaporize, mixing with ejected material from other planetary collisions or with solar wind-driven debris. This could strip away lighter mantle material, leaving behind a denser iron-rich core. In extreme scenarios, tidal forces from the expanding Sun could generate enough stress to fracture the planet internally, triggering large-scale geological collapse or even fragmenting the planet into multiple smaller bodies that either continue orbiting the Sun or are ejected into interstellar space. Earth's ultimate form could be radically altered, its mass redistributed, and its structural integrity compromised beyond recognition. The interactions with other surviving planets and debris during this stage further complicate Earth's fate. As Venus and Mercury are destroyed, fragments of these planets may collide with Earth, compounding the destructive effects of heat and tidal stress. The gravitational dynamics of the inner solar system will be in flux, as mass loss and orbital shifts create an environment ripe for collisions, scattering, and chaotic motion. Even if Earth is spared direct destruction, these interactions could strip material from its surface or destabilize its orbit over millions of years, further diminishing the planet's capacity to retain its current form or support any semblance of life. The expansion of the Sun into a red giant marks the beginning of the final, inexorable countdown for life on Earth. Long before the planet is physically engulfed or its orbit dramatically altered, the increasing luminosity and heat from the swelling star will trigger a cascade of environmental catastrophes that systematically eliminate life across the globe. Scientists have been able to model the timeline for this extinction process with a surprising level of detail based on our understanding of solar evolution, planetary climate dynamics, and biological tolerances. The results paint a sobering picture. Life on Earth will not wait for the ultimate destruction of the planet, but will be eradicated gradually as the Sun's energy output steadily climbs over millions of years. The first signs of life-threatening conditions will appear approximately 1 billion years from now. During this time, the Sun's luminosity is projected to have increased by about 10%, enough to push the Earth's climate into an extreme greenhouse state. Global temperatures will begin to rise steadily, causing a slow but relentless evaporation of oceans and a disruption of weather patterns. Photosynthetic organisms, which form the foundation of Earth's biosphere, will be among the first to suffer. Plants and algae require a narrow range of sunlight and temperature to carry out photosynthesis efficiently, and the rising heat will damage cellular structures and metabolic processes. As photosynthesis falters, the oxygen supply in the atmosphere will gradually decline, triggering a chain reaction that destabilizes entire ecosystems. Multicellular life, including animals, will be indirectly affected as their food sources disappear and environmental stresses mount. Roughly 1.5 billion years into the Sun's continued brightening, the increasing solar flux will make Earth's surface nearly uninhabitable for complex life. Oceans, already shrinking due to rising temperatures, will begin to vaporize more rapidly, leading to higher concentrations of water vapor in the atmosphere. This water vapor acts as a greenhouse gas, trapping heat and accelerating the planet's warming in a feedback loop that scientists refer to as a moist greenhouse effect. At this stage, surface temperatures could reach several hundred degrees Celsius in equatorial regions, far beyond the limits of survival for even the hardiest extremophiles known today. Marine ecosystems will collapse, terrestrial habitats will dry out or become molten, and the diversity of life will plummet dramatically. By the time the Sun begins its rapid expansion into a red giant, several 100 million years after entering the red giant precursor phase, most remaining life on Earth will be extinct. Microbial life that can survive in extreme conditions, such as deep-sea hydrothermal vents or subterranean environments, may persist slightly longer. However, even these refugees will be threatened as surface heat penetrates deeper into the crust and oceans boil away entirely. Volatile loss from the atmosphere and hydrosphere, combined with the destruction of chemical cycles that support life, ensures that no ecosystem remains intact. The habitable zone, once comfortably encompassing Earth, will have moved outward beyond Mars, leaving the planet isolated in a zone of lethally high radiation and heat. As the Sun swells further during the red giant phase, Earth's last surface life forms will be eradicated. The ocean's evaporation will leave behind vast salt plains and exposed seabeds, while the atmosphere becomes dominated by water vapor, carbon dioxide, and trace gases released from the breakdown of rocks and organic material. Any remaining organic molecules will be degraded by intense ultraviolet radiation and energetic solar particles from the amplified stellar winds. Within this window of tens of millions of years, the final vestiges of life on Earth will be destroyed, long before the planet itself faces engulfment or extreme orbital displacement. The process is gradual and relentless, a natural consequence of the Sun's evolution and the intrinsic vulnerability of life to stellar forces. The timeline for the extinction of life also illustrates the relative fragility of ecosystems on geologic and cosmic scales. Life has persisted on Earth for approximately 4 billion years, surviving asteroid impacts, ice ages, and fluctuating climates. Yet the slow and steady brightening of the Sun will prove far more destructive over long timescales. Unlike sudden catastrophes, the gradual heating gives life no opportunity to adapt fully, as the changes occur too uniformly and comprehensively across the planet. Even extremophiles, which thrive in extreme temperatures, pressures, or chemical conditions, are unlikely to survive the combined effects of heat, radiation, and atmospheric depletion, highlighting the inevitable nature of life's demise in a maturing solar system. It is important to recognize that these events will unfold over hundreds of millions of years, a time frame far beyond human perception, but relatively short in cosmic terms. By the time Earth experiences total sterilization, the Sun will be fully committed to its red giant phase, radiating far more energy than at any other point in its history. Oceans will have completely vanished, continents will be molten or fractured, and any remaining atmosphere will be thin, superheated, and unrecognizable. Life, once a resilient and diverse phenomenon, will have been extinguished completely, leaving Earth as a barren, inhospitable rock orbiting an enormous dying star. As the Sun's red giant phase progresses, the drama of its evolution intensifies at the very heart of the star, its core. After exhausting its hydrogen fuel in the central regions, the Sun's core becomes predominantly helium, supported only by the pressure of degenerate electrons and the residual thermal pressure from prior fusion. This core, no longer able to sustain hydrogen fusion, contracts under its own gravity, and as it shrinks, temperatures and pressures escalate to astonishing levels. Eventually, conditions become extreme enough to ignite helium fusion, a process fundamentally different and far more energy-intensive than hydrogen fusion. This marks the beginning of the Sun's transition from a hydrogen-burning star to a helium-burning one, a critical stage that reshapes both the internal structure of the star and the fate of the surrounding solar system. Helium fusion occurs through the triple alpha process, where three helium nuclei, also called alpha particles, combine to form a single carbon nucleus, and in some cases, an additional fusion step produces oxygen. This process requires temperatures exceeding roughly 100 million Kelvin in the core, which is many times hotter than the Sun's current central temperature during its main sequence stage. Because helium nuclei are more tightly bound and possess a double positive charge, they naturally repel each other, making fusion of helium much more difficult than the fusion of hydrogen. Only under these extreme temperatures and pressures can the electrostatic barrier be overcome, allowing nuclei to collide with sufficient force to fuse. Once fusion begins, the process generates vast amounts of energy that counteract the core's contraction, temporarily stabilizing the Sun and halting the rapid collapse that would otherwise continue. The ignition of helium in the Sun's core is not a subtle or gradual event, but rather occurs as a violent phenomenon known as the helium flash. Because the core is degenerate, meaning the pressure depends largely on the density of electrons rather than temperature, the initial fusion of helium does not immediately expand the core. Instead, helium fusion starts in a runaway reaction, releasing an enormous burst of energy in a relatively short time. This energy is quickly absorbed by the surrounding layers, which are still non-degenerate, causing the core to expand and the outer layers of the Sun to contract slightly. The helium flash represents a turning point in the Sun's life cycle, halting core collapse and stabilizing energy production for the next phase of its evolution. While this event is catastrophic on the nuclear scale, it will not be noticeable from Earth, given that the planet is already in an uninhabitable state by this time. Following the helium flash, the Sun settles into a period of relative stability known as the horizontal branch, during which helium fusion proceeds steadily in the core, converting helium into carbon and oxygen. This phase lasts for tens to hundreds of millions of years, a relatively short period compared to the main sequence, but long enough to dramatically alter the internal structure of the star. The core is surrounded by shells of hydrogen that continue to undergo fusion, creating a layered configuration, a helium-burning core at the center, an inner shell of hydrogen fusion, and an outer convective envelope. This stratified structure governs the Sun's energy output, luminosity, and expansion, while also dictating the intensity of stellar winds and the distribution of material throughout the solar system. The energy released from helium fusion is immense, but because the red giant's outer layers are already so extended, the increase in luminosity is distributed over a vast surface area, slightly tempering the outward radiative effects compared to the earlier main sequence. The chemical byproducts of helium fusion, carbon and oxygen, are significant for multiple reasons. Internally, these elements accumulate in the Sun's core, gradually building a dense, inert carbon-oxygen core that will remain after helium is exhausted. Externally, some of this material will eventually be expelled into space during the later stages of the Sun's life, seeding the interstellar medium with the elements essential for the formation of new stars, planets, and even the building blocks of life. This stage demonstrates the fundamental role that stars play in cosmic chemical evolution. The death of one star lays the foundation for the birth of future generations. The carbon and oxygen produced in the Sun's core today will persist long after the star's surface has cooled and faded, contributing to the next cycle of stellar and planetary formation. The onset of helium fusion also triggers a change in the Sun's physical appearance. As the core stabilizes, the outer envelope of the Sun contracts slightly from its maximum red giant dimensions, while the overall luminosity may remain high. Surface temperatures may increase marginally, altering the color of the star from deep red to a slightly more yellow-orange hue. This contraction of the outer layers reduces the threat of immediate engulfment for planets at the edge of the Sun's expansion, although the inner solar system remains a hostile and uninhabitable environment. The energy released from the core continues to drive strong convection in the outer layers, sustaining powerful stellar winds that continue to strip planetary atmospheres and redistribute material into space. Eventually, helium in the core will be depleted, leaving behind a dense carbon-oxygen core that cannot ignite further fusion under the Sun's mass. Unlike more massive stars capable of fusing heavier elements, the Sun lacks sufficient mass to initiate carbon fusion, ensuring that the core will remain inert and set the stage for the next major phase of its evolution, shedding its outer layers to form a planetary nebula. The helium burning phase, therefore, represents both a period of intense internal activity and a prelude to the Sun's final acts. It transforms the core's composition, redistributes energy throughout the star, and governs the dynamics that will dictate the ultimate fate of the solar system. Following the Sun's helium-burning phase, its life enters a stage of dramatic transformation, the shedding of its outer layers to create what astronomers call a planetary nebula. Despite the misleading name, planetary nebulae have nothing to do with planets. The term arose historically because these glowing shells of gas, when first observed through early telescopes, resembled small, rounded planetary disks. In reality, a planetary nebula represents one of the most visually striking stages of stellar evolution. A luminous, intricate halo of gas and dust expelled by a dying star. For the Sun, this phase will begin after its core has exhausted helium and can no longer sustain further nuclear fusion. The outer layers, no longer supported by the energy generated in the core, become unstable and are ejected into space, leaving behind the dense, hot core that will eventually become a white dwarf. The process of forming a planetary nebula is both complex and mesmerizing. The Sun's outer envelope, now distended from the red giant phase, becomes increasingly tenuous and pulsates due to internal instabilities. These pulsations, combined with radiation pressure and strong stellar winds, drive the ejection of the outer layers into space over tens of thousands of years. Unlike the slow, gentle loss of solar mass during earlier red giant stages, this expulsion occurs in distinct, episodic bursts. Each pulse throws off shells of gas that expand outward at velocities of tens of kilometers per second, forming concentric layers that can interact and create intricate patterns of density and motion. Dust grains, heavier elements, and molecules embedded in these shells contribute to their opacity and structure, producing stunning visual textures that can be observed across vast distances in the galaxy. The expelled material becomes ionized almost immediately by the intense ultraviolet radiation emitted by the hot, exposed core left behind. This ionization is what gives planetary nebulae their characteristic glow. Atoms in the gas are stripped of electrons, and as these electrons recombine, they emit light in various wavelengths. The resulting colors are dictated by the chemical composition of the expelled material. Hydrogen produces deep reds, oxygen contributes vibrant greens and blues, and nitrogen adds to the reddish-orange hues. The interplay of these elements, combined with density variations and shock waves from interacting shells, creates the iconic, intricate shapes that make planetary nebulae among the most visually stunning objects in the cosmos. Each nebula is unique, its structure shaped by the dynamics of the dying star, magnetic fields, and interactions with binary companions if present. The Sun's planetary nebula will extend far beyond the current orbit of Neptune, forming an expanding halo of luminous gas that can be seen from light years away. While the formation of the nebula itself will take tens of thousands of years, a blink of an eye on cosmic timescales, the structure will persist for tens of thousands more, slowly dispersing into the interstellar medium. This halo represents the Sun's final act of interaction with the cosmos. The mass lost from its outer layers enriches space with the elements created in its interior, including carbon, oxygen, and traces of heavier elements formed during fusion. Over time, this material contributes to the chemical evolution of the galaxy, providing the building blocks for future stars, planets, and potentially life elsewhere. In this way, the planetary nebula is not only a magnificent visual spectacle, but also a critical mechanism in the recycling of cosmic material. The planetary nebula is not a permanent fixture. It represents a transitional stage in the life of the Sun. As the outer layers expand and diffuse into interstellar space, the core left behind continues its evolution into a white dwarf. Nevertheless, the nebula remains one of the most enduring and visually impressive legacies of a star like the Sun. Its radiant glow, spanning multiple light years, will illuminate the interstellar medium, a testament to the Sun's chemical contributions and a spectacular final farewell visible to distant observers in the galaxy. The interplay of colors, motion, and chemical composition ensures that the Sun's planetary nebula will be remembered not only as a scientific phenomenon, but also as a cosmic artwork, a radiant signature of the life and death of a star. As the Sun completes the process of shedding its outer layers to form a planetary nebula, the result is nothing short of a cosmic masterpiece, a breathtaking light show that will mark the star's final moments as a visible, energy-emitting body before it settles into the quiet life of a white dwarf. This spectacular halo of gas and dust is the culmination of billions of years of stellar evolution, a moment when the Sun's internal life and outer expression converge to create one of the universe's most awe-inspiring phenomena. From the perspective of a distant observer, the Sun will no longer appear as a solid, shining disk, but as a glowing sphere surrounded by ethereal, multicolored shells that drift into the vastness of space, illuminated by the exposed core's intense ultraviolet radiation. The colors seen in this cosmic display arise from the ionization of the elements that the Sun has forged over its lifetime. Hydrogen, the most abundant element in the ejected material, emits a deep crimson light as its electrons recombine, producing the classic red hues often associated with nebulae. Oxygen, ionized by the intense radiation from the hot core, contributes vivid greens and blues, creating stunning contrasts against the red background. Nitrogen adds subtle orange and reddish tones, while other trace elements such as neon, sulfur, and carbon produce additional nuances, giving each planetary nebula a unique palette. The interplay of these colors is not uniform. Density variations, turbulence in the ejected shells, and shock waves from overlapping layers create intricate patterns, filaments, and knots that appear almost sculpted, as if the sun's final energies are being painted across the void of space. The outer layers of the sun, now free from the gravitational binding of the core, expand and drift outward at thousands of kilometers per hour. Over tens of thousands of years, these layers will grow to enormous scales, spanning distances that dwarf the orbits of the outer planets. As they move away from the intense gravity and radiation of the sun, the gas cools and interacts with the interstellar medium, forming glowing filaments and halos that can be observed from many light years away. From Earth, if any observer still existed, this display would be a fleeting but astonishing sight, a final cosmic farewell that conveys both the beauty and inevitability of stellar death. The Sun, once a stable yellow star, transforms into a radiant, multicolored beacon, its final luminosity amplified by the combination of expansion, radiation, and ionized material in motion. What makes this display particularly extraordinary is the scale of both space and time. Unlike transient phenomena like supernovae or solar flares, the Sun's planetary nebula will persist for tens of thousands of years, slowly diffusing into the interstellar medium while retaining its vivid colors and structure. Over billions of years, the expanding shell will fade as the gas disperses, yet for the duration of its visible life, the nebula will outshine entire star fields in its immediate vicinity, serving as a luminous testament to the Sun's existence and its ultimate transformation. The patterns and colors of this glowing cloud are a direct consequence of the Sun's life history. The elements created through billions of years of nuclear fusion now dance outward, glowing under the influence of ultraviolet radiation from the still hot core. The final glow is more than just a visual spectacle. It represents a profound moment in cosmic evolution. As the Sun sheds its outer layers, it is not merely dying, but also contributing to the broader cycles of the universe. Carbon, oxygen, and other elements essential for life are carried outward, seeding nearby regions of space that may one day form new stars, planets, and potentially life itself. In this sense, the Sun's final light show is both an ending and a beginning, a beautiful transient phenomenon for observers in the present, and a lasting gift to the future universe. The ethereal glow of the expanding nebula, with its reds, greens, blues, and delicate filaments, is the star's ultimate legacy, a reminder of the intricate and interconnected processes that govern the life and death of stars. The spatial dynamics of this light show are also remarkable. Interactions between multiple shells of ejected material produce shock fronts that compress gases, creating brighter regions where the radiation is concentrated. Stellar winds continue to sculpt the nebula, pushing some regions outward more rapidly while allowing others to lag, forming arcs, loops, and filamentary patterns that seem almost intentionally artistic. The visual diversity is immense. No two planetary nebulae are identical, even if the parent stars were similar in mass and composition. For the Sun, this final light show will be a singular event, one that humanity cannot witness directly, but can imagine through the study of other stars at this stage. This cosmic farewell also emphasizes the scale of time and mortality in the universe. The Sun's final glow will persist far longer than human civilization has existed or is likely to exist. while billions of years will pass before the outer layers fully disperse. This halo of gas and dust remains a record of the Sun's life, a glowing memory etched into the interstellar medium. Each filament of gas, each ionized pocket of hydrogen or oxygen, tells a story of billions of years of nuclear fusion, convection, and cosmic transformation. It is a reminder that the death of a star is not a quiet or singular event, but a long, multi-layered process with far-reaching consequences that extend across both space and time. After the Sun has completed its dazzling display as a planetary nebula, what remains at its center is the dense, hot remnant of the once massive star, the white dwarf. This core, stripped of all its outer layers, represents the final stable state for stars of the Sun's mass, a stellar ember that no longer undergoes nuclear fusion, but radiates the residual heat accumulated over billions of years. Approximately the size of Earth, yet containing nearly half the Sun's original mass, the white dwarf is an extraordinary example of matter compressed to extreme densities. A teaspoon of this material would weigh tons on Earth, illustrating the remarkable transformation from a vast, radiant star to a compact, highly dense object. In essence, the Sun has completed its nuclear life cycle, and the white dwarf phase represents the long-term, slowly fading presence of the star in the cosmos. The formation of a white dwarf occurs as the carbon-oxygen core left behind after helium fusion ceases contracts under gravity. Without sufficient mass to ignite carbon fusion, the core stabilizes through electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed into the same energy state. This pressure halts further collapse, allowing the core to maintain a stable size while retaining enormous density. Unlike the dynamic and luminous stages of the Sun's earlier life, the white dwarf no longer generates energy through fusion. Instead, it shines by radiating the stored thermal energy from its earlier life. Initially, a newly formed white dwarf has surface temperatures exceeding 100,000 Kelvin, making it extremely luminous in the ultraviolet and visible spectrum. Over time, this heat will slowly dissipate into space, but for billions of years, the white dwarf remains a brilliant point of light, a faint echo of the Sun's former glory. Despite its small size relative to the Sun's original volume, the white dwarf's mass ensures that its gravitational pull remains substantial. It will continue to exert a stabilizing influence on the outer remnants of the solar system, maintaining the orbits of distant planets, comets, and asteroids that survive the red giant phase. The lack of nuclear fusion means the star will no longer produce powerful stellar winds, allowing the previously ejected planetary nebula to drift away into interstellar space. However, the gravity of the white dwarf ensures that loosely bound material in the vicinity may remain trapped, forming a faint disk of gas or dust in some cases. This residual structure can persist for millions of years, slowly accreting onto the white dwarf or dispersing further, subtly reshaping the remnants of the Sun's planetary system. The physical properties of the white dwarf are remarkable and extreme. Its density is so high that matter behaves in ways entirely unlike ordinary planetary material. The electrons in the core are forced into a degenerate state, creating pressures far beyond those found in any terrestrial environment. The interior is essentially a crystal lattice of carbon and oxygen nuclei, immersed in a sea of highly degenerate electrons. This composition ensures structural stability despite the immense gravitational forces at work. Furthermore, the small size of the white dwarf relative to its mass means surface gravity is thousands of times stronger than that on Earth, crushing any hypothetical nearby object under extreme tidal forces. This stark contrast between size, mass, and density highlights the transformative power of stellar evolution and the ability of quantum mechanics to support matter under conditions that would otherwise be impossible. The white dwarf also serves as a slowly fading beacon of the Sun's existence. Initially, it will be incredibly bright due to residual thermal energy, but over the course of billions of years, it will radiate its heat into space and gradually cool. Unlike earlier stages of stellar evolution, there is no ongoing energy generation to replenish this heat, so the luminosity declines steadily. As the white dwarf cools, it moves from white-hot through shades of yellow and red, eventually becoming a faint, dark remnant. During this cooling process, the white dwarf remains a gravitational anchor for any surviving bodies in the solar system, influencing the orbits of distant planets, dwarf planets, asteroids, and comets. Its presence ensures that the solar system, though dramatically altered, retains a coherent structure long after the Sun's visible light has faded. Another remarkable feature of the white dwarf phase is its extreme longevity. While active fusion in stars lasts billions of years, the cooling process for a white dwarf takes tens to hundreds of billions of years. During this time, it will gradually approach thermal equilibrium with the surrounding space, fading ever more slowly. This prolonged persistence makes the white dwarf a cosmic relic, a remnant of the Sun that will endure far beyond the lifespan of any remaining planetary structures or biological history associated with Earth. Essentially, it represents the enduring footprint of our star, a dense, silent witness to the Sun's past life and the evolution of the solar system. The transformation into a white dwarf also emphasizes the inevitability of the Sun's life cycle. Stars like the Sun lack the mass necessary to end their lives in dramatic explosions such as supernovae, and instead follow a more subtle, yet no less profound path to stellar retirement. The creation of a white dwarf ensures that the Sun's core is preserved, maintaining its elemental composition while shedding its outer layers. This stark contrast between the catastrophic events of supernovae in massive stars and the comparatively serene transition of a Sun-like star underscores the diversity of stellar death pathways in the universe. The white dwarf stage is a quiet, stable, and long-lasting conclusion to the star's dynamic life, providing an enduring record of its nuclear history. Once the Sun has transitioned into a white dwarf, the most striking change is the dramatic slowing of its activity. Without nuclear fusion to generate energy, the white dwarf begins a long, steady process of cooling, gradually fading in brightness over billions of years. Initially, the newly formed white dwarf is extremely hot, with surface temperatures exceeding 100,000 Kelvin, radiating a brilliant white-blue light. However, this luminosity is entirely derived from the residual thermal energy retained from the Sun's previous life stages. Unlike during the main sequence or red giant phases, where fusion actively replenished energy, the white dwarf has no internal energy source. As a result, it becomes a slowly dimming beacon in space, a silent testament to the Sun's former vibrancy. Over time, as it radiates heat into the surrounding void, the star's temperature declines, and its color shifts from white-blue to yellow, orange, red, and eventually towards invisibility. The cooling process is governed by the principles of thermodynamics and the physics of degenerate matter. The white dwarf is incredibly dense, with a carbon-oxygen core stabilized by electron degeneracy pressure. This density means that the white dwarf has a very high heat capacity relative to its small size, allowing it to retain thermal energy for extraordinarily long periods. Because of this, the cooling is remarkably slow, stretching over tens of billions of years. As the heat radiates outward through the thin atmosphere of the white dwarf, the surface temperature gradually drops. The luminosity of the star decreases correspondingly, following a predictable curve where the decrease in brightness slows further as temperatures decline. The fading white dwarf, once dazzlingly hot, becomes a faint, glowing ember suspended in the void, a cosmic relic of a star that once dominated the solar system. During the early cooling phase, the white dwarf still emits significant ultraviolet and visible light, which may temporarily illuminate the remnants of the planetary nebula before it disperses into interstellar space. Over time, however, as the outer layers of the former Sun disperse and the surrounding nebula fades, the white dwarf becomes increasingly isolated, visible primarily to instruments capable of detecting faint infrared radiation. The cooling trajectory is affected by the composition of the white dwarf, the presence of residual elements in its thin outer layers, and crystallization processes occurring in the core. As the white dwarf cools, the carbon-oxygen core gradually begins to crystallize, forming an incredibly dense and rigid lattice structure that further slows the rate of heat loss. This crystallization releases a small amount of latent heat, slightly prolonging the white dwarf's glow and extending its visibility in the cosmos. Over billions of years, the white dwarf will continue this slow fade, gradually approaching equilibrium with the temperature of the surrounding space, which is currently just a few degrees above absolute zero. Its luminosity will decrease from roughly 1,000th of the Sun's present brightness in the early cooling stages to an almost imperceptible glow, eventually rendering it invisible to the naked eye. The timescale for this transformation is so vast that it far exceeds the current age of the universe, meaning that white dwarfs formed in the early history of the cosmos are still in the process of cooling today. The Sun's white dwarf will follow a similar trajectory, acting as a long-lasting monument to the star's life, preserving its mass and elemental composition even as it becomes ever colder and darker. This cooling process also has implications for the solar system's remaining structure. While the white dwarf no longer produces stellar winds or intense radiation, its gravitational influence remains significant, anchoring the orbits of any surviving planets, dwarf planets, and cometary bodies. The absence of strong stellar activity, however, means that no new energy input affects these objects, and they drift through space in a relatively stable, albeit altered, solar system environment. The cooling white dwarf is effectively a silent overseer of the remnant system, its gravitational presence shaping the long-term dynamics of planets and minor bodies, while it itself fades toward invisibility. Eventually, the Sun's white dwarf will approach a state of near-total darkness, its temperature converging toward the ambient temperature of the interstellar medium. At this stage, often theorized as the black dwarf phase, the star will no longer emit significant radiation of any kind. However, this stage is purely theoretical, as the universe is not yet old enough for any white dwarf to have cooled to this extent. For billions of years before reaching this state, the white dwarf will continue to shine faintly, a slowly dimming remnant visible to distant observers with sensitive instruments. This prolonged cooling phase emphasizes the enormous timescales of stellar evolution, highlighting that even in death, stars like the Sun remain active participants in cosmic dynamics over unimaginable stretches of time. When the Sun has completed its transformation into a white dwarf, the solar system will be a very different place from the orderly, life-filled system we know today. The once bright, life-sustaining star will be reduced to a faint, Earth-sized ember, still exerting gravity but stripped of its energy and radiance. The planets, asteroids, comets, and other remnants of the solar system will all feel the effects of this transition in profound and lasting ways. The most immediate impact will be due to the Sun's mass loss during its red giant and planetary nebula phases. As the Sun sheds nearly half of its original mass, its weakened gravitational hold will cause the surviving planets to drift outward into wider orbits. This shift alters the entire structure of the solar system, stretching distances and destabilizing delicate orbital resonances that had held for billions of years. The inner planets, Mercury, Venus, and very likely Earth, will be gone by this time, consumed or destroyed during the red giant phase. Mars may survive, but in an altered orbit, far removed from the Sun's faint glow. The gas giants, Jupiter and Saturn, will remain as the most dominant bodies in the system, along with Uranus and Neptune, though their orbits too will expand significantly. Without the Sun's former mass anchoring them as tightly, their paths will grow larger and more elliptical over time. This expansion increases the likelihood of orbital instabilities, particularly among the outer planets, leading to potential ejections of smaller moons, asteroids, or comets into interstellar space. The once stable balance of the solar system becomes a more chaotic environment, where the white dwarf is no longer the powerful center, but instead a weakened anchor presiding over a stretched and thinned planetary system. Asteroids and comets, which once thrived in belts and clouds bound tightly by the Sun's gravity, will also be deeply affected. The asteroid belt between Mars and Jupiter, already disrupted by Jupiter's gravitational dominance, will experience additional instability. Many asteroids will be nudged into new orbits, some colliding with planets, others escaping the solar system entirely. The Kuiper belt, home to icy bodies beyond Neptune, will expand outward, and its population will scatter further into space. Even more dramatically, the Oort cloud, the vast spherical reservoir of comets extending light years from the Sun, will be only loosely bound to the remnant white dwarf. With the Sun's diminished gravity, many of these comets will be stripped away by passing stars or the tidal forces of the Milky Way, effectively bleeding the solar system of its icy outskirts over cosmic timescales. Another significant effect will be the potential destruction of some smaller bodies that wander too close to the white dwarf. Although the Sun's mass has decreased, its compact size means its surface gravity is still immense. Any asteroid, comet, or even remnant planetesimal that strays too close risks being torn apart by tidal forces in a process known as spaghettification. The debris from such tidal disruptions can form temporary accretion disks around the white dwarf, creating rings of dust and gas that periodically brighten the otherwise faint star. Astronomers studying other white dwarfs have observed such dusty disks, along with heavy elements polluting their atmospheres. Clear evidence that planetary remnants are occasionally consumed by their collapsed parent stars. In this sense, the Sun's white dwarf phase may still be an active participant in shaping its surroundings, even billions of years after its prime. The surviving planets themselves will face bleak futures. Jupiter and Saturn, the gas giants, will cool in the absence of solar energy, their cloud tops growing darker and less dynamic as heat from the white dwarf provides only a faint glow. Their many moons will also grow cold and inert, with any subsurface oceans freezing solid over time. Uranus and Neptune, already icy worlds, will drift further into darkness, their atmospheres eventually stabilizing into frozen stillness. If Mars survives, its surface will be frozen beneath thick sheets of carbon dioxide and water ice, bathed only in the dim light of the white dwarf. None of these worlds will support active geology or atmospheres in the way they once might have under the Sun's warmth, leaving them as frozen, silent relics orbiting a fading ember. Yet in the midst of this cosmic quiet, there remains a strange beauty. The solar system will still exist, albeit in a ghostly, altered form. The giant planets will orbit like sentinels around the white dwarf, while distant icy bodies wander in stretched paths, some falling away into the galaxy. The faint glow of the white dwarf may occasionally be brightened by the destruction of an unlucky asteroid or comet, creating momentary bursts of light in the otherwise dim system. Over eons, the system will continue to thin as objects are ejected or collide, gradually leaving behind only the most stable survivors. The solar system, once a vibrant and dynamic place teeming with energy and life, will eventually become a sparse, quiet collection of frozen worlds orbiting a fading star. In this long-term view, the transformation of the solar system reflects the natural cycles of stellar and planetary evolution. The planets and smaller bodies will no longer be bathed in the sun's brilliance, but will remain gravitationally tied to the remnant, slowly orbiting in silence as the white dwarf cools. The once bright, active system becomes a cosmic relic, a reminder of the processes that shaped it, and an example of the fate that awaits countless other star systems across the galaxy. In time, the sun's white dwarf will fade further, and the surviving planetary system will dissolve into the broader fabric of the Milky Way, its story etched into the chemical and gravitational patterns of the universe. The death of the sun will not be the end of its story, but rather a transformation, a continuation of the great cosmic cycle that governs the universe. The gas and dust ejected during its red giant and planetary nebula phases will not drift away in vain. Instead, this material, rich with elements forged inside the sun's core, will merge back into the interstellar medium, the vast sea of gas and dust that fills the Milky Way. Hydrogen and helium will still make up the bulk of this debris, but it will also carry heavier elements like carbon, oxygen, nitrogen, and traces of metals. These ingredients are the building blocks of everything we see, from planets to oceans to the molecules of life itself. The sun, which once sustained Earth, will scatter its essence into the galaxy, ready to give rise to new worlds. Stars are often called the factories of the universe because they take simple elements and fuse them into complex ones, but their true power comes from what happens after they die. The enriched material they release becomes the raw fuel for the next generation of stars. Somewhere, perhaps millions of years after the sun's planetary nebula fades, a dense region of interstellar gas might collapse under gravity, and within it, the atoms once held tightly in the sun could find themselves part of a newborn star. Around this young star, disks of dust and gas could clump together into planets, and within those planets, chemistry could unfold in intricate ways, eventually giving rise to new forms of life. In this sense, the sun's death will ensure that it continues to live on, not as a burning sphere in our sky, but as a contributor to the next wave of cosmic evolution. The idea that Earth itself, along with every living being, is made of star stuff is not poetic exaggeration, but scientific truth. The carbon in our DNA, the calcium in our bones, the iron in our blood, all of it was created in the hearts of long-dead stars that came before the sun. Just as we are made from the remnants of ancient suns, so too will future civilizations, perhaps far beyond our galaxy, inherit the material released by our sun. This means that the sun's legacy will not vanish into darkness. It will be encoded into new systems, new worlds, and perhaps new intelligent beings who one day gaze up at their skies and wonder about their origins. But the recycling of the sun's matter is not just about creating new stars and planets. It is also about the ongoing evolution of the Milky Way itself. The galaxy is alive in a sense, constantly reshaping itself through the birth and death of stars. Supernovae enrich it with heavy elements like gold and uranium, while stars like the sun contribute essential life-giving elements like carbon and oxygen. Over billions of years, this process gradually changes the chemical makeup of the galaxy, ensuring that each new generation of stars forms in an environment richer and more diverse than the one before. When the sun dies, it will join countless others in this eternal process, helping to sculpt the future of the Milky Way. It is humbling to think that while humanity may vanish long before the sun releases its final breath, the atoms that once formed our bodies will remain part of the universe's grand narrative. They may travel light years across the galaxy, pulled into a new stellar nursery, eventually forming the soil of another planet, where rivers flow and skies shimmer with alien constellations. And if life emerges there, it will carry within it a direct connection to us, a lineage not of species, but of stardust. The sun's final gift, then, is not destruction, but renewal. Its passing ensures that the cycle continues, that creation follows destruction, and that the universe remains ever dynamic, ever alive. The sun has been our anchor, our guardian, and our light for billions of years. But when its time ends, it will take its place among the silent architects of the cosmos, shaping a future it will never see, but forever influence. The story of the sun is not only the story of Earth's rise and fall, but also the story of the universe itself, written in fire, dust, and the endless recycling of stars. As the sun enters its late stages of life, one of the most profound changes it will undergo is the gradual but relentless loss of its mass. This is not a sudden process, but a slow unraveling that begins long before the sun becomes a red giant and intensifies dramatically during its final phases. Right now, even in its stable main sequence stage, the sun is already shedding mass through a continuous outflow of charged particles known as the solar wind. Every second, it loses millions of tons of matter, carried away into interplanetary space. Although this sounds enormous, compared to the sun's total mass, about 333,000 times the mass of Earth, it is a tiny fraction, not nearly enough to affect planetary orbits in noticeable ways. Over billions of years, however, this subtle process adds up, setting the stage for much larger changes to come. When the sun begins its transformation into a red giant, its outer layers will expand and its stellar winds will grow exponentially stronger. This period marks a turning point as the solar wind becomes a gale powerful enough to strip away enormous amounts of material, blasting it outwards into space. In fact, during this phase, the sun is expected to lose nearly half of its mass. Gravity is intimately tied to mass, and the sun's immense gravitational pull is what keeps the planets locked in their orbits. As its mass decreases, its gravitational grip weakens, and this has sweeping consequences for the entire solar system. The orbits of the planets, which today are relatively stable, will begin to drift outward. Without the same gravitational anchor holding them tightly, Earth, Mars, and the outer planets will spiral farther from the sun. For Earth, this shift may come too late to save it from being swallowed or scorched beyond recognition during the red giant expansion. But for the outer planets, the story is different. Jupiter, Saturn, Uranus, and Neptune will all migrate to wider orbits, altering the balance of the solar system. This change could have ripple effects across billions of years, reshaping the architecture of the system in ways both subtle and profound. The smaller objects in the solar system, the asteroids, comets, and icy bodies of the Kuiper belt, will be even more affected. Their orbits, already sensitive to gravitational shifts, could be dramatically perturbed as the sun's mass dwindles. Some may be ejected from the solar system entirely, flung into interstellar space as rogue wanderers, no longer bound to the faint ember of the white dwarf sun. Others may collide with one another or be drawn into unstable resonances with the giant planets, leading to cascades of new impacts and disturbances. The solar system will not be destroyed outright, but it will never again resemble the orderly clockwork it does today. Another consequence of the sun's mass loss is the change in its Hill sphere, the region around it where its gravity dominates over the pull of neighboring stars in the galaxy. Currently, the sun's Hill sphere extends for trillions of kilometers, enclosing the Oort cloud, the vast reservoir of icy bodies thought to surround the solar system. As the Sun sheds mass, its Hill sphere will shrink, and many of these distant icy objects will drift free, severed from the Sun's influence. Some may wander into the galaxy as orphaned comets, while others could be captured by the gravity of passing stars. In this way, the Sun's dying breath contributes not only to the recycling of material into the interstellar medium, but also to the reshaping of its immediate galactic neighborhood. The weakening of the Sun's gravity will also mean that the delicate balance of planetary interactions will shift. Today, the orbits of planets are stabilized by the combined effects of the Sun's gravity and their mutual gravitational tugs. As the Sun loses mass, these dynamics will become more complex. For instance, the giant planets, now in wider orbits, may exert stronger perturbations on the outer solar system, potentially destabilizing regions of the Kuiper belt or Oort cloud. Over vast timescales, this could trigger waves of comets plunging inward long after Earth is gone, a cosmic echo of the Sun's transformation. It's worth noting that not all planets are equally affected. The gas giants, with their immense masses and deep gravity wells, will likely remain intact, continuing to orbit the Sun's white dwarf remnant, albeit in altered paths. Smaller bodies, however, may not be so fortunate. Moons orbiting these planets could find their orbits destabilized as their host planets drift outward. Some moons may escape entirely, becoming independent bodies orbiting the Sun or wandering into space. Others could crash into their parent planets, adding a final flourish of chaos to the solar system's reshaping. In a broader sense, the Sun's mass loss is a reminder of how interconnected everything in the solar system truly is. The Earth's oceans, Jupiter's moons, the icy objects on the solar system's fringes, all are bound together by the invisible thread of gravity, woven by the Sun's mass. As that thread weakens, the entire tapestry shifts. This is not a sudden collapse, but a gradual reweaving, a process that unfolds over millions and billions of years, long after life on Earth has vanished. Yet despite all these dramatic changes, the solar system will not dissolve entirely. Instead, it will settle into a new, quieter configuration, a white dwarf sun at its center, orbited by the surviving planets on wider, slower paths, surrounded by a sparse halo of comets and asteroids, many of them altered or displaced. It will be a system forever changed, but still a system, carrying the faint echo of the star that once blazed so brilliantly at its core. In the unimaginable stretches of cosmic time, far beyond anything our species or even our planet could ever witness, the white dwarf remnant of the Sun will slowly make its way toward its ultimate and theoretical end stage. A white dwarf, despite its small size, roughly that of Earth, is blisteringly hot when it is first born, with surface temperatures reaching upward of 100,000 degrees Kelvin. This incredible heat glows brightly, making the star appear as a brilliant, compact jewel in the night sky. But unlike normal stars, a white dwarf has no fusion at its core to replenish this heat. It shines only by radiating away the thermal energy it already possesses, like a piece of iron pulled from a forge, cooling slowly in the open air. The process, however, unfolds not over minutes or hours, but across trillions upon trillions of years, as the dwarf gradually loses its glow and fades into darkness. As it cools, the white dwarf passes through stages of dimming, becoming less radiant with each passing eon. At first, it is still bright enough to be detected by distant civilizations, if any remain, shining with a faint blue-white glow that eventually softens into a dull red ember. Over billions of years, it transitions into an object so faint it would be nearly impossible to see with even the most advanced telescopes. Its surface would solidify as the atoms within it compress into a strange, crystalline structure. In fact, astronomers predict that as white dwarfs cool, their carbon and oxygen atoms begin to crystallize, essentially turning the star into an immense cosmic diamond. If our Sun follows this path, then in the far future, its core may literally become a gem the size of Earth, a diamond floating silently in space. Eventually, in time spans so vast they make the current age of the universe seem fleeting, the Sun's white dwarf will radiate away almost all of its heat. It will cease to glow in any visible spectrum, its light lost to the cosmos. At that point, it will no longer be a white dwarf, but a hypothetical black dwarf, a stellar corpse so cold and faint it is virtually invisible. No such objects exist yet, because the universe itself is still too young. Our cosmos is only about 13.8 billion years old, and white dwarfs require quadrillions of years to cool into black dwarfs. This means the black dwarf stage is purely theoretical at this point, a destiny predicted by physics but not yet observed. The Sun's transformation into a black dwarf would take longer than the universe has existed so far, underscoring just how vast and incomprehensible these cosmic timescales truly are. A black dwarf would be the quiet end of the Sun's journey, a final resting state where it exists as a cold, dark ember. Without light or heat, it would exert influence only through gravity, continuing to pull faintly on the surviving planets and objects that remain in its orbit. It would be a ghost of a star, the remnant of what once lit the solar system with brilliance and power. For Earth, if it somehow survived the red giant phase and remained in orbit around the white dwarf, the black dwarf Sun would mean eternal darkness, a frozen and barren wasteland circling a star that no longer shines. The concept of the black dwarf also touches on the fate of the universe itself. In a far future often called the heat death scenario, all stars will eventually exhaust their nuclear fuel and fade into remnants like black dwarfs, neutron stars, and black holes. Over unfathomable timescales, even those remnants may undergo further changes, with black dwarfs slowly evaporating protons through processes predicted by quantum physics, such as proton decay, if such phenomena indeed occur. In this view, the Sun's ultimate fate is part of a universal trend towards stillness and darkness, where energy is evenly spread and no new stars are born. This final phase of the Sun may be almost impossible to imagine, not only because of the extraordinary timescales involved, but because it represents an end so quiet and complete that it contrasts starkly with the Sun's fiery birth and vibrant life. From a blazing ball of fusion energy that gave rise to planets, oceans, and life, it will become a cold relic, a monument to time itself. The black dwarf, though unlit, symbolizes not a failure, but the natural conclusion of stellar evolution, a reminder that even stars, for all their brilliance, are temporary fixtures in the cosmos. The fate of our Sun, while dramatic and transformative, is ultimately a relatively quiet one compared to the explosive deaths that await larger, more massive stars. The Sun's destiny is to swell into a red giant, shed its outer layers, and leave behind a white dwarf that cools into obscurity. But stars that are several times more massive than our Sun live shorter, more violent lives and die in cataclysmic events that reshape galaxies. These differences arise because the life cycle of a star is determined primarily by its mass. Mass dictates how much pressure builds in the core, how quickly nuclear fusion proceeds, and how the star eventually meets its end. Take, for example, stars at least 8 times the mass of the Sun. Their greater mass produces vastly higher pressures and temperatures in their cores, which means they burn through their nuclear fuel much faster. Instead of enjoying a long, stable main sequence phase like the Sun's 10 billion year stretch, these massive stars might last only tens of millions of years before reaching exhaustion. When their hydrogen runs out, they move rapidly through stages of helium fusion, then carbon, oxygen, neon, silicon, and beyond. Each stage burns progressively faster, leading to the formation of heavier and heavier elements until iron is created in the core. Iron is a dead end for fusion. It doesn't release energy when fused, which causes the delicate balance between outward pressure and inward gravity to collapse catastrophically. This collapse triggers one of the most dramatic events in the universe, a supernova. In a matter of seconds, the star's core implodes while its outer layers explode outward with unimaginable force. The resulting blast can shine brighter than an entire galaxy, releasing more energy than the Sun will emit over its entire 10 billion year life. The material flung into space enriches the cosmos with heavy elements like gold, uranium, and iodine, elements essential for planets and life as we know it. Our Sun will never undergo such a violent death. It lacks the mass to collapse with that intensity. Instead, its end will be comparatively gentle, though no less significant to the planets that orbit it. From the wreckage of a massive star's core, two possibilities emerge, depending on its mass. If the core is between about 1.4 and 3 times the mass of the Sun, it collapses into a neutron star, an object so dense that a single teaspoon of its matter would weigh as much as a mountain. Neutron stars are extraordinary, with powerful magnetic fields and rapid rotation rates that create pulsars, lighthouses of radiation sweeping through space. But if the core exceeds about 3 solar masses, the collapse cannot be stopped by neutron pressure, and the result is a black hole, a region of space-time so warped by gravity that not even light can escape. Black holes are among the most mysterious and extreme objects in the universe, capable of devouring matter and even merging with one another to send ripples of gravitational waves across the cosmos. Comparing this to the Sun highlights just how diverse the universe's stellar life cycles can be. Our Sun will not collapse into a neutron star or black hole. It doesn't have the mass required. It will leave behind a white dwarf, a dense but relatively modest remnant, shining faintly with residual heat. While less dramatic than a supernova, the Sun's end is still profoundly important because it demonstrates the pathway for the majority of stars in our galaxy. Most stars are like the Sun, medium-sized, steady burners that will conclude their lives as planetary nebulae and white dwarfs. In fact, supernovae and black holes, while spectacular, are relatively rare compared to the quieter deaths of stars like our own. Yet, though the Sun's end will not shake galaxies with explosive force, it remains no less awe-inspiring. It serves as a reminder that the universe thrives on cycles. Massive stars enrich the cosmos with heavy elements through supernovae, while stars like the Sun contribute in quieter ways, spreading their gases into interstellar space to seed future stars and planets. Each type of stellar death plays a role in shaping galaxies, in creating the building blocks of life, and in driving the evolution of the cosmos itself. In this grand symphony of creation and destruction, the Sun's quieter fate is not lesser. It is simply one variation in the universe's vast tapestry of stellar endings. When we contemplate the final fate of the Sun, it is tempting to view it only through the lens of loss, the end of Earth, the extinguishing of light, and the eventual silence of a once vibrant star. Yet, within this ending lies a story that is far greater than destruction. It is a story of transformation, continuity, and cosmic renewal. The Sun's death will not be the end of everything, but rather a step in the eternal cycle of stellar life, where endings become beginnings and remnants become seeds for new worlds. Every particle of the Sun that is released into space, every fragment of gas cast off during its red giant phase, will become part of the raw material from which future stars, planets, and even life itself may emerge. In this sense, the Sun's death is not a final chapter, but a contribution to the universe's ongoing narrative. Philosophically, the life of the Sun reflects a profound truth about existence itself. Stars are born, they shine, they give of themselves, and eventually they fade. Humanity too exists within this same rhythm: birth, growth, decline, and transformation. Just as the Sun has nurtured life on Earth for billions of years, providing the energy that allowed simple cells to evolve into complex beings capable of thought and wonder, so too will its eventual passing serve a higher purpose. The elements forged within its fiery heart, carbon, oxygen, nitrogen, are the very elements that make up our bodies, our atmosphere, and our oceans. When the Sun disperses its material into space, it will return these elements to the cosmos, ensuring that its essence endures long after the star itself has faded. This cyclical nature of cosmic evolution invites us to think of the universe not as a place of permanent endings, but as a continuum of transformations. The death of stars enriches galaxies. The cooling of remnants sets the stage for new generations of stars. Even the blackest dwarf in the far future will still be part of this grand process, its gravity influencing passing objects, its atoms eventually finding new homes in interstellar clouds. Life after the Sun, then, is not bound to Earth or humanity, but to the wider universe, where the legacy of our star will ripple outward for eternity. What is truly awe-inspiring is how the universe recycles itself in ways both violent and gentle, weaving together explosions, collapses, and quiet dissolutions into a tapestry of creation. Without the deaths of stars, there would be no heavy elements, no planets, no water, no life. Without the Sun's eventual shedding of its layers, the raw material for new stellar nurseries would be diminished. The cosmos thrives precisely because stars must die, and it is through this inevitability that life itself becomes possible. The Sun's story is our story, for without it, neither Earth nor we could ever have existed. And so, when we think of the Sun's death, we should not imagine only darkness or despair. Instead, we can see it as a grand farewell, a breathtaking transformation in which our star contributes to something larger than itself. Long after we are gone, long after Earth is either swallowed or abandoned, the atoms of our Sun will drift into the galaxy, perhaps to take part in the birth of a new solar system, perhaps to become part of beings who one day look up at their own star with wonder. In this way, the Sun achieves a kind of immortality, not as an eternal flame, but as an eternal source, living on in the stars, planets, and lives yet to come. The death of the Sun reminds us that nothing in the universe truly ends. Stars burn out, galaxies collide, and even the cosmos itself may someday fade into stillness. But at every stage, there is transformation, recycling, and renewal. Life after the Sun is not an absence, but a continuation of this eternal dance. And within that truth lies something deeply humbling and profoundly beautiful. We are part of a universe that is alive, dynamic, and ever-evolving. The Sun's final act is not a tragedy. It is a gift to the cosmos, a reminder that even endings blaze with purpose, and that from the ashes of stars, life will always find a way to rise again. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.